We're getting close. We're getting close. Gotta get your papers out. Try to get off the phone. We're getting close. We're gonna start right in here in a little bit. Get organized. Come on. We're gonna go right from the chute. Come on. You can do it. We're at 3:59. We're gonna start here at number 9 on the quiz. All right. We know the test is a week from today, right? We know the test is a week from today. It will be close to getting everything done today. Close. We might have a little smidge to finish up Tuesday, but we'll be close. Okay. All right, let's do number 9. A person makes iced tea by adding 1.8 kilograms or 1,800 grams of hot tea at 80. How many kilograms of ice? Oh, kilograms of ice initially at 0 are required to bring the mixture to 10. Okay. So we know Q lost is equal to Q gain. The 1,800 grams times the specific heat of 4.184 joules per gram degrees Celsius. It's going to bring it from 80 down to 10. It's going to end up at 10. We know that's going to change by 70 degrees Celsius. But the gain of heat is going to involve 2 things. We first have to melt the ice. First thing we got to do is melt that ice, correct? We can't get it to 10 if we don't melt it first. So we got to melt it first, which is going to be the mass. Oh, that's what we're looking for. The mass times the enthalpy of fusion for ice, which I believe is 333. I believe it's 333. Plus, now that melted ice, we have to take, once we melt it, it's at 0, correct? Once we melt it, we got to take it, we got to increase it 10 degrees, correct? So that's going to be that same mass times the specific heat of that water, because we have it melted. And my temperature change here is 10. So that will allow you to combine like terms, basically combine the M terms on the right or factor out an M. combine M terms or factor out an M. 11. This is, we're going to raise the melted ice 10 degrees, right? After it's melted, we got to raise it up 10 degrees. Okay, in 11, what do we got here in 11? 10 kilograms. I'm going to change that to grams immediately, being 10,000 grams. What do we got here? How much heat in kilocalories? So we can convert that to kilocalories when we get all done. We've got 10,000 grams of aluminum at 30. Oh, we got to melt it. Okay. So we have aluminum solid at 30 degrees Celsius. We have to melt it. We have to get it to aluminum solid, stays solid, no phase change, at its melting point temperature of 660. Oops. Then we got to turn it into aluminum liquid. Right? We got to get it from 30 to 660, and then we got to melt it. That's still going to be 660 degrees melted. So it looks like we've got two. All we're going to do is melt it, right? Yeah. Yeah, we're just going to melt it. So this part right here is going to be MC delta T. And this part right here is going to be mass times the enthalpy of fusion. And we can just add those. We can just add those up. Okay, last time we did this calculation here, where we took ice at -50, I believe. We did this big calculation here, ice at -50 up to vapor at 200. What is the biggest amount of heat involved? Boiling away the water. Changing liquid water at 100 to gas at 100 takes a lot of heat energy. It looks like I skipped this. Did I skip this at the bottom of 8 here? I did. So at the bottom 8, I guess we better do this. Oh. We're just going to melt that. So that's just going to be a phase change at the bottom of 8. So Q is going to be my mass times my enthalpy of fusion. I think it's already at the melting point, huh? How much heat is needed to melt completely? 20 grams of silver at its melting point. Yeah, it's already at its melting point. So we are simply going to have 20.0 grams. And my enthalpy of fusion is 88.2 joules per gram. So 880 to 1764, I think, if my brain's working. $17.64 if we did sig fig $17.60. Huh? Okay. We are now on chapter 5, part 2, right here. And the title of this is the first law of thermodynamics. Now, so it's hard to find something that you can really relate to, but this is a good example here. This is a great example. This is a tablespoon of dry ice. What is dry ice? What is dry ice? Dry ice is solid carbon dioxide, CO2, solid. The cool thing about it is it doesn't melt. It goes directly from a solid to a gas. It goes directly from a solid to a gas. Kind of like those ice cubes. If you leave them in the freezer for a long time, they shrink, don't they? They go from a solid to a gas. They don't melt inside your freezer. What is freezer burn? It's taking moisture out. It's going directly from the solid to a gas. It doesn't happen very rapidly, but for dry ice, it does. So I have a tablespoon of dry ice. I put it into a Ziploc bag. I seal it. And this happens if I put a book over top of it. It's a great example. What's going to happen is this is going to go from CO2 solid to CO2 gas, correct? It's going to have to absorb some heat energy to do that. It's going to take some heat energy to do that. Where is it going to take the heat energy from? The surroundings. Then we also say that if we can raise something up like this, we've done some work. That would accomplish some work. What's the classic definition of work? Force times distance. Won't talk physics in here. What's the classic definition of work? You applied some force over some distance. We could accomplish some work done. Yes, we could get this thing to do some work for us. It would raise the book up for us. So it would have to absorb some heat and it would do some work for us. That is the first law of thermodynamics. When a system exchanges energy with its surroundings, in this case, the surroundings is going to supply some heat energy in the form of work or heat. The first law may be written as this change in internal energy like this, or I like to do change in E. I don't like energy being U, but this is kind of interchangeable. Depends upon your book. My change in energy is my E here or my U here, change by triangle, internal energy. And Q is the energy transferred as heat energy to or from the system. And W is the work transferred as work or to or from the system. So we have to talk heat energy and we have to talk work. Okay, let's go to the next page. Oh, I'm sorry. Before we go to the next page, let's look at this word right here. Energy is absorbed. We're going to be looking at words like this. Energy is absorbed. It does work on the surroundings. Okay. On the next page, here's our sign convention on the next page. Again, it's simply my change in energy is equal to Q plus W. This is heat to or from the surroundings. This is work. Now, this would be no different here than, and we talked about this previously, if I put just regular ice in that bag, it's going to melt. Yes. How's it going to melt? It's going to take energy from the surroundings. Yes. It's going to take energy in from the surroundings. Okay. So we've got to make sure we just keep track of our sign convention here. If Q is less than 0, or excuse me, Q is greater than 0, just like previously, we know that this is endothermic. The same sign conventions as before. It's endothermic then. The system absorbs heat. Think of that just as melting ice. It's going to absorb heat. Energy is added to the system. Think of this right here as heat in. Now, it's going to increase the internal energy of the system. If I have solid ice in there and it melts, those molecules are going to be moving faster, correct? As it goes from a solid to a liquid, that would be an example of increasing the internal energy. Well, previously we did Q less than 0, and we know that that is exothermic. And if something is exothermic, think of that as heat out. System loses energy. Heat out. Heat out. So that would decrease the internal energy. Okay. Work. Work is greater than 0 if the surroundings do work on the system. So think of this as work in. And that is going to increase internal energy of the system. And then if work is less than 0, think of work out. Okay. If we go back to our example, then the system here is what's inside my bag, correct? The system is what is inside my bag. Energy is absorbed. Q is greater than 0. We are putting heat in, correct? From the surroundings. Heat is going into that system, and we can get some work out of this, correct? So if we get work out, work is less than 0. Okay. Again, heat and work. What does heat do? Heat always affects the internal speed of the molecules inside, typically internal energy. Ammonium nitrate, commonly used as fertilizer, decomposes explosively. Now, you can Google some of those explosions. They've blown up entire towns. Storing ammonium nitrate fertilizer. It is a fantastic fertilizer. Why is it a fantastic fertilizer? Because the percent nitrogen in it is really high. It's a great, great nitrogen fertilizer. Okay, so now if this explodes, we're just going to look at this. If this decomposes explosively, do you think you can get some work out? You think you can raise a book by blowing the damn thing up? We can raise the roof on this building, correct? We can for sure get work out of this. If we get work out, work should be less than 0. So my first question is work positive, negative, or 0? Work should be negative. If work does not equal 0, is work done on the system or by the system? Now, think of that explosion taking place in my Ziploc bag, if you will. That is the system. The work is going to get done by the system. So the final result, work is negative and work is done by the system. All right, so here's some OWL questions that relate to this. An automobile provides 515 joules of work. Work out or work in? That's going to be work out. It provides that much. Work out. So my work then is negative 515 joules. How does an automobile work? Put gasoline in it, gas enters the pistons, and there's an explosion in there. Yes? There's an explosion in that cylinder. It generates 277 joules of heat. Is that heat out or heat in? That's heat out, correct? Is that positive or negative? This is heat out. So this should be negative 2277 joules. Calculate the change in internal energy. My change in energy, Q plus W. So it looks like we'd have negative 2277 joules plus a negative 515 joules. Negative. Yeah, I can do it. 2792. Negative. Better forget my. All right. So we've got a negative. This is an exact question from Al. Negative 2792. Okay. A chemical reaction is run in which 551 joules of heat is absorbed. Heat in or heat out? Absorbed is going to be heat in, yes? Heat in. Heat is Q, so Q going to be positive or negative? Heat in. Positive. 551 joules. All right. The internal energy changes by 405 joules. So my change in energy is 405 joules. Oh, I laid this out here. I'm not sure why, but. So if we have change in energy is equal to Q plus W. We're just solving this for how much work we get here for work. And if we solve that for W, we subtract that from both. Oh, we're going to get a negative. Negative 146 joules is equal to our work, huh? All right. Now, let's go on to the next page. And now what we're going to talk about is how much heat energy reactions absorb or produce. We know there's heat energy reactions in our body because that keeps our body temperature at 98.6 or so. Yes? It's a lot of energy, internal energy, keeping our blood and everything circulating at 98.6. That's a lot. Where's the energy come from? Food, right? Comes from our food calories. Where's our food get the energy from? Well, if you go right down to it, if you're eating nuts or vegetables and stuff like that, where's the energy come from? The sun, yeah, photosynthesis, all that stuff, huh? It absorbs the energy. Okay, now instead of Q, we got to change things because that'd be too easy. The heat content of a chemical reaction is symbol H. What is the word for that? Enthalpy. Enthalpy, enthalpy, enthalpy. Enthalpy is just the heat of reaction, right? How much heat can we get for a reaction? Delta H then is the change in enthalpy. I thought Q was heat of reaction. Well, at constant pressure, our Q really is equal to delta H. Delta H is enthalpy. Okay. Eventually, we're going to calculate our heat this way. It's going to be our enthalpy is going to be product heat minus reactant heat. Products minus reactants. Now, enthalpy is a state function. What is a state function? Definition: a property of a system that is determined only on the initial and final states or conditions of the system and not on the path taken on going from the initial state to the final state. For example, if I look at this map and I want to go from Los Angeles to Salt Lake City, all I care about is getting there. I can take this path, this path, this path. It doesn't matter. All I care is I started here and I ended up in Salt Lake. That's a state function. It doesn't matter. Okay. So you're going to see now some heats for reaction. And here is an example here. I'm not sure how I ended up with this one down here, but I did. Okay. This is page 245. We know, I have demonstrated this in class, if we combine hydrogen plus oxygen to make water, we get some heat out of that thing. Yes? So hydrogen plus oxygen to give us water. Now, it makes a difference whether or not we put the water as a gas or a liquid, different heat contents. Delta H, the heat for R for that reaction, and this little sign right here means standard state conditions, usually 25 degrees Celsius and normal atmospheric pressure. That little degree sign really means standard conditions. It's negative 241.8 kilojoules per mole. Well, you probably could figure out, I could calculate how many kilojoules of energy based upon the grams then, correct? If we could burn so many grams, we could go grams to moles, and then we could figure out how much energy we need. Energy would be evolved, right? We're going to get energy out. Okay, let's look at the next page. Oh, and by the way, let's go back to that. I'm sorry. It's probably the first time you've seen this. I don't think we've ever balanced with a half, right? We've never balanced with a half. Some books will do that. You can balance with a half, but that's kilojoules per 1 mole here. 1 mole here. It would be a half a mole there, just from the balanced equation. Well, if it was 1 mole to produce that, what if you had 2 moles? If you had 2 moles, you just would double your energy output. So if I had 2 here instead of 1, and I did not use the half, if I balanced it with the 2, I would get negative 483.6 kilojoules per mole. Now, the states solid, liquid, gas matter. Different heat contents. Different heat contents. If you reverse the reaction, you reverse the signs. So, for example, if you're going to combine hydrogen plus oxygen to produce water. This is exothermic. You're going to get heat out. If I reverse the reaction, I'm going to have to put heat in. Now, what does it look like if I reverse it? Well, if I reverse the reaction, I'm going to have H2O liquid. I would get H2 gas plus 1/2 O2 gas. I just reversed it. What's delta H going to be? It's going to be positive 285.8. So instead of getting energy out, I would be putting energy in. Okay. I want to do this example. I'm going to skip this example. I'm going to go to 5-6. Table sugar can be oxidized to carbon dioxide and water. So C12H22 plus 12O2, I get 12CO2 plus 11H2O. This reaction is negative 5645 kilojoules per mole. We would get this heat energy out, correct? Heat energy out. This just looks like a combustion reaction, right? Just looks like a combustion reaction. Well, what is the enthalpy change when you burn 5 grams of sugar? So we'll start right here. 5 grams of sugar. You're going to need to write this down. Because this is in kilojoules per mole. Well, how many moles is 5 grams would be logical, correct? How many moles in 5 grams? So 1 mole and if I add up 12 carbons, 22 hydrogens, 11 oxygen, right? $342.34 grams. Then I get minus 5645 kilojoules per 1 mole. This one we got to keep track of right here. There is a 1 there, really, if we balance the equation, huh? We got to keep track of this is in kilojoules per mole. So my grams cancel out, my moles cancel out. This would be minus 82.4 kilojoules I would get out. Okay. Obviously, this 5 grams is way. If I wanted to get this much energy out, I'd have to burn perfectly a mole, 342.34 grams. Okay, now look at the balanced equation here. My delta H is in kilojoules per mole, but there's no 1 here for any of them. So we just got to keep track of from our balanced equation. How much heat would we get out? We're going to get heat energy out again. It's negative. What is the enthalpy change for 15 grams? Just a reminder, 12.01 and 1.01, right? You still remembered that anyway. 12.01, 1.01, completely dead microphone. That's what I thought. Right. Okay. I think we're back in business. Doesn't sound like it though. How many grams in a mole? 1 mole C2H6 grams. 24.02, 6.06, 30.08. This gets us negative 228.57.3 kilojoules. For 2 moles. So we would get negative 712 kilojoules. All right, this would make more sense here. So we're going to use the same reaction and we're going to calculate how many grams you would need to release a certain amount of energy. In this case, 775 kilojoules. If we're going to release that, it's going to be negative 775 kilojoules. And my energy is negative 2857.3 kilojoules. To mole. And then 1 mole of C2H6. .08 grams. All right, I'm not going to do that example up there. Let's go to the next page. So Al does a lot of this, which is Hess's law. Now, Hess's law works, and we'll use Hess's law if we have a reaction that's going to take way too long, or it's too dangerous, you don't have the supplies to do it. It turns out we can add and subtract reactions to get the one we want. So again, reactions that are slow, reactions too slow, dangerous, do not have the supplies. We're going to do that in lab in 2 weeks, not the next lab, the week after that. Next week's lab, we're doing gas stoichiometry, but we are doing Hess's law the week after that. Okay, so this works best if you have a highlighter. Grab some highlighters if you've got them. So we want this reaction here. We want how much heat for this reaction, and we're going to combine these two. So I'm going to grab a highlighter and my H2O gas here that I want is here. And my other color I'm going to use, it doesn't matter what color. Here I have H2O liquid, and here I have H2O liquid. So here's what I need to do. I like my blue because the reaction I want, I have 2 H2O liquid on the right as a product. This I have 2 H2O liquid right there. So I like that. I'm going to leave that one alone. Again, I'm trying to get this net reaction out of these two. What am I going to have to do with reaction 1, though? I'm going to have to reverse that. I need to get my H2O gas not as a product. I need it as a reactant. So I am going to, I'm going to bring number 1 down, and I'm simply going to reverse it. If I reverse number 1, I end up with 2 H2O gas now as a reactant. And if I reverse it, I need to change that sign, correct? So instead of releasing 486 joules of energy. I'm going to end up putting that in. This is now going to be positive 483.6 kilojoules. Reaction number 2, I'm going to rewrite it just because I think it just works out better. That's going to stay the same. I'm just going to rewrite it. Now, don't get too big because we're going to add these all together here. So that one's going to stay the same. I'm going to have 2 H2 gas plus O2 gas, 2 H2O liquid. I've got that there, and my number is correct. I have my H2O gas over here, and that numbers are correct. The rest of them are going to cancel. So the rest should cancel out. I have 2 H2 gas as a product here. I have 2 H2 gas as a reactant here. Kind of like having 2X on both sides of the equal sign. I'm going to put a light X on them. And I've got O2 gas on the product side here. And I've got O2 gas on the reactant side here. So when I add them together, it's kind of like doing net ionic reactions. 2 H2O gas to 2 H2O liquid. My delta H for this reaction, when I add these up, is going to be negative 88.1. Owl takes you into this really slowly. Like Owl will say, well, what's the enthalpy change if I reverse it? Well, what's the enthalpy change if I multiply by? Owl leads up to this pretty slowly. So with Owl, you're going to have reactions where they just reverse it or multiply it by 2 or something like that. Okay, now let's do the next one. Take a highlighter. We need 3 colors. We've got PCl3 liquid. Oh, this sucks already. It's on the wrong side. We've got P4 solid. And we've got Cl2. Now again, oops, where's my Cl2? What the heck? I got it in both places, huh? This has got some ugliness to it. Okay. The P4 solid looks good. It's on the reactant side here, what in the reaction we want, and it's on the reactant side here. That looks good. The Cl2, right now, if I added these up, I'd have 11 of them, correct? On the left. But I got 4 PCl3. I only have 1 PCl3 here. What am I going to do with this reaction? I'm going to reverse it, and I'm going to multiply it by 4. Okay. So we'll draw an arrow right here. For this reaction, we're going reverse times 4. So I am going to have 4 PCl5 solid, right? That's this reversed. And I'm putting a 4 there. I'm multiplying. I'm going to put a 4 in front of all these. 4 PCl3 liquid. 4 Cl2 gas. I'm going to get 4 times the amount of energy, and I got to switch the sign, right? Still on the screen? No. We're just going to go kilojoules from. Okay, reaction number 1. We're going to bring it down and do nothing with it. But I'm going to rewrite it. P4 solid, 10 Cl2 gas, 4 PCl5 solid, and I guess I should put my little. So I like what I'm seeing, because my Cl2 is going to work, right? The Cl2 looks like the rough one. So if I draw my line, I think I've got it. Now, there is more than one way to do these. This isn't the only way to do them. But it looks like my 4 PCl5 here is going to cancel out on both sides. I'm going to grab my red pen here. Those are going to cancel. I have 10 Cl2 on the reactant side, 4 on the product side. Cross out the 4, change that 10 to a 6, correct? I'm going to cross that out completely. I know that this is going to turn into 6 Cl2 gas. I got to take 4 times that, which is going to be about 494.4. I'm still going to get a negative value here. Negative 1278.8. The next one's an easy owl one. Well, no, I don't know if this is an owl. So the next one is easier than the one we just did. So in the next one, we've got N2 right here. So that looks promising already. We've got O2 right here. And then we have NO2. What's the only thing we got to do? We could do this one quickly. There's a coefficient of 2 here, correct? We're just going to multiply this one through by 2. And I'm going to do it right here. I'm not going to rewrite this. We're going to go times 2 on this one. So I'm going to put a 2 here in red. I'm going to multiply this by 2, which I can do, no problem. This would be 2 times 1/2. And I'm going to multiply this by 2. And I'm going to multiply this times 2. And I think I can just add it up, right? My 2NO now is going to disappear, right? 2NO on both sides. And this O2, 2 times 1/2 is 1, correct? 2 over 2 are 1, so I've got this. I'm going to have N2 gas plus 2 O2 gas, 2 NO2 gas. Make sure we're multiplying this one by 2. Next page. Three equations. So what? 3 equations. Carbon solid. Oh, that looks nice right off the bat. We've got H2 gas. Ooh, that's not so bad. It's on the same side at least. And then we've got CH4 gas. Ooh, that's on the wrong side. Am I missing? Yeah. We're going to reverse number 3 right away. Get this CH4 on the product side. We're not going to multiply it because it's just a 1 there, right? So we're going to reverse. We're going to reverse this reaction. So we're going to end up with CO2 gas plus 2 H2O liquid gets us CH4 gas, ooh, plus 2 O2 gas. Did I do that right? Yes. So if we reverse this, positive 890.3. Reaction 2, what are we going to do? We got to go times 2, correct? We got to go times 2 because of this 2 right here. So we're just going to go times 2. So it's going to be 2H2 gas plus 2 times 1/2 O2 gas gives us 2 waters. What about number 1? We'll bring her down the same, leave it the same. Okay, I think number 1, I want to rewrite it down here, and it should just be the same, huh? So we have carbon solid. Now I'm going to highlight again. Everything you do not highlight has to cancel out, right? Everything you do not highlight needs to cancel out. So everything else needs to cancel here. All right, let's see what we've got. The CO2 is an easy one. CO2 here and CO2 here for sure. Two waters here. And two waters here. Two O2 here, one O2 and one O2. So both of those are going to go, right? This is one O2 plus one O2, which is two O2. So we've got it. And we have exactly what we need. We've got carbon solid, 2H2 gas, CH4 gas. We're going to have to add all three of these up, making sure we've multiplied this one by 2. And that's going to produce minus 74.8 kilojoules. Last one. This one caused me liver damage because I grabbed this out of a first edition of a textbook one day. And that 1/2 was missing, which made it impossible to solve. And after an hour and a half, I figured out it was impossible to solve. Maybe it was longer than an hour and a half. I don't know. But let's highlight this. Let's see what we got here. We've got CLF gas. We've got F2 gas. CLF gas. We've got CLF gas. We've got F2. Where in the heck? Ooh, F2 is over here. CLF3, these look pretty similar. CLF3 right here. All right, let's see what you can do. We'll have to solve this now. Next time now Al doesn't even give you a 3 equation 1. Al thinks you're not smart enough. I don't know. I know you're smart enough to do that. If you look at the test outline, Hess's law questions come up, I believe 4. A 1, a 2, a 3, or I don't know. Well, there's quite a few Hess law. We will do this next time we meet. And then we're going to be this and this. We're going to be done next time. You need to bring chapter 6 then. On this quiz, you should be able to do through 16. So you're only going to have 2 left on the quiz. You now should be able to do 1 through 16. Bring chapter 6 with you next time, and we'll be in the chapter 6 next time. Test Thursday, right? Week from today.